All right, so now we're going to go into trig functions. Are trig functions well behaved? What do I mean by that? Are they continuous throughout the whole function? Well, let's think about sine, right? Think about your sine graph. It just continues forever, right? Both directions. So I can take the direct substitution anywhere in a sine graph. Totally fine, right? Cosine graph, same thing, right? I can do direct substitution to find my limit anywhere, okay? What about tangent?
You can't do it.
You can't do it anywhere, right? The only place you can do tangent is when it's in the domain, okay? So that's the key part. It has to be in the domain there. So you have to see that part where it is a real number in the domain. So what numbers are not in your domain of tangent? Where are your asymptotes for the tangent graph? Pi over 2s, 3 pi over 2s, 5 pi over 2s. So none of those values would work. But as long as you're finding a C here and you're plugging it in where it does exist, then you just do direct substitution for all your trig functions. Okay? So again, these are going to be examples where we can just do direct substitution. So let's try that first one. Limit as x approaches 0 of tangent of x. Well, let's plug it in. What's the tangent of 0? Tangent of 0. Ooh, we got to get our unit circles out again. It is just 0. We're good. Think about your graph. Okay, for this one, again, I can just do direct substitution because it's multiplication. So I'll have pi times cosine of pi. What is the cosine of pi? Negative 1. So then it's pi times negative 1, and my answer is negative pi. How about for this one? Plugging in a 0. It's just the sine of 0 squared. What's the sine of 0? 0. What's 0 squared? 0. And that's it. Okay, so trig functions, you can use direct substitution. All right, last page. Functions that agree at all but one point. I'm recording right now, and you people are acting like payasos. Theorem 1-7. Right. You're not on TV. Anyone, these are the graphs, so what am I talking about? When it agrees in all but one point. Okay? Basically, the graphs are exactly the same except for one point. Usually what this means is it's got a hole. Okay? When something has a hole, you can just evaluate it as if it didn't have a hole. Because the limit is going to be the answer to where that hole is, right? Your limit is going to be the y value of the hole. So that's all you have to do. So let's look at example 6. I'll walk through it. This is obviously a rational function. Let's simplify this. How do you factor a quadratic? X minus 1, x squared, plus x, plus 1. Same, opposite, positive. Remember how to factor cubics? X minus 1. What happens? Cancels, and I get a hole. What are the coordinates of my hole?
1, 0.
Positive 1, because remember you take this, change the sign of the one you canceled out, right? It's the root of the one you canceled. So positive 1, and then how do I get my y value? Plug it back into this remaining function. So that's 1 plus 1 plus 1, which is 3. Okay? So my hole is at 1, 3. If I think about this graph for a second, right? This is a parabola. My vertex, trust me, is over here at negative 1/2. Okay, so it looks something like this. But there's a hole at 1, 3. So if I think about the graph of that, what is the limit as x is approaching 1 of this graph? What's the limit? What's my y value that I'm getting close to? I'm getting close to 3, right? So all that it's saying is that you will always just evaluate anytime you've got a hole and you're asked to find the limit at that x value, your answer for the limit is just going to be your y value. Okay? So my limit is like, well, what value should it be if there wasn't a hole there? It should be at 3, right? So my limit as x approaches 1 of this entire graph is just 3. Okay, it's always that y value. Okay? All right, so overall, let's kind of recap what we did. A strategy for finding limits. The first part, recognize which limits can be evaluated by direct substitution. So give me a few. What are the types of graphs that can be evaluated by direct substitution? What did we talk about today? Which ones? Linear would work. What else? Other ones that you can just do direct substitution. Come on, give me more. It'd be what? Well-behaved graphs, like, starts with a P. Yeah, or quadratics, polynomials. Starts with an R. Radicals, rationals. Okay. How about trigs? Can we do trigs? Yeah, your basic trig functions are fine. Later on, we're going to talk about some weird trig functions tomorrow, but basic trig functions work. So all of these just nice, normal functions that are continuous throughout, we can evaluate by direct substitution. If the limit cannot be evaluated by direct substitution, try to find a function that agrees with everything except at c. This is the whole idea, right? So when it's got the whole, again, you just have to do the y value of your whole. And lastly, if you need to, you can always go back to graphing or numerically. So graphing or tables to reinforce your conclusions that you get, okay? The one graphs that kind of don't fit in here are those piecewise graphs that we talked about, right? So piecewise ones aren't going to be a nice linear quadratic polynomial. They're not going to be any of these. So those you're going to have to look at graphically usually, okay? All right, example 7 is very similar to example 6. Please try it. Factor that. Notice I can't use direct substitution because what would happen if I use direct substitution? What if I plugged in a negative 3? My denominator would equal 0, right? Because denominator would equal 0. So I can't use direct substitution, which means I need to factor. Yeah, and what do we know? There's going to be a hole, right? What are the coordinates of my hole? -3. Careful. And that's not 1 now. -3, -5. Yeah, because it's got to be negative. So you got to switch the sign, plug it back in, and we get -5. So what is my limit? As x approaches -3, what's my limit? -5. Yeah, it's just equal to the y value, right? You could graph this. This is just a line, and it's got a hole in it, okay? But right at that hole, that's where we're going to try to find the limit. All right, last example, and I'm going to go back and talk about the homework from last night because the last problem on the homework was kind of like this one, where what am I going to do with this guy? Because again, if I try direct substitution, it's going to make my denominator 0, right? Substitution. All right, because that would make my denominator 0. So I can't do direct substitution. So what do I do with this guy? Well, one of the techniques that you can use is to rationalize the numerator. Okay, how about that for weird, right? There was a kit way back when, earlier in the year, where you had to rationalize the numerator. And you were like, why do we have to rationalize the numerator? Isn't the point to get them out of the denominator? Why are we putting them back into the denominator? Well, in situations like this, in calculus, rationalizing the numerator is going to become very helpful. So how do we rationalize this numerator? Well, let's write it out. We've got square root of x plus 1 minus 1 all over x. How do I rationalize the numerator? Just the same way you would have rationalized a denominator. So I want to multiply by its conjugate. What's the conjugate? Big word. What's that mean? Opposite. Change the sign. Yes. So what am I going to write? Square root of x plus 1 plus 1. That's exactly right. Over square root of x plus 1 plus 1. And now here's the magic. What happens on the top? No radical anymore. It's just x plus 1. My middle two terms cancel out. All right, I have plus root x plus 1 minus root x plus 1. And then my last two, -1 times 1 is just -1. So what do I end up getting on the top here? X. Those cancel, right? So just X. The bottom, don't work out your bottom. Just leave it as X times that whole thing. Why do I want to keep it like that? Because what's going to happen to those X's now? Gone. And so then what am I left with? 1 over square root of X plus 1 plus 1. Can I now do direct substitution with a 0? Yeah, isn't that awesome? I can plug in a 0 and I don't have a denominator equal to 0 anymore. So now I can actually get an answer. I can get my limit. Life is good. Good. So now can do direct substitution. Okay. So again, this is sort of a weird one, right? I couldn't plug it in. It would make it 0, so I've just got to now do 0 plus 1 plus 1. What do you guys get? 1 over 2. Perfect. So my limit, and you could check this on the graph. Now you could graph this and see, is it really true that as X is approaching 0, I'm getting really, really close to 1/2? Is that true? And yes, it would be true if you looked at it on the graph. Okay? But this is really the only way to figure this guy out. And we're done. Questions? Okay, I want to go over some stuff from homework last night. So let me just turn this off and then we can, hold on.